Simple Network Management Protocol is an Internet standard protocol for managing devices on IP networks. Devices that typically support SNMP include routers, switches, servers, workstations, printers, modem racks and more. SNMP is used mostly in network management systems to monitor network-attached devices for conditions that warrant administrative attention. SNMP is a component of the Internet Protocol Suite as defined by the Internet Engineering Task Force. It consists of a set of standards for network management, including an application layer protocol, a database schema, and a set of data objects. SNMP exposes management data in the form of variables on the managed systems, which describe the system configuration. These variables can then be queried by managing applications. Overview and basic concepts. In typical SNMP uses, one or more administrative computers, called managers, have the task of monitoring or managing a group of hosts or devices on a computer network. Each managed system executes, at all times, a software component called an agent which reports information via SNMP to the manager. SNMP agents expose management data on the managed systems as variables. The protocol also permits active management tasks, such as modifying and applying a new configuration through remote modification of these variables. The variables accessible via SNMP are organized in hierarchies. These hierarchies, and other metadata, are described by management information bases. An SNMP managed network consists of three key components: managed device, Agenta Euro software which runs on managed devices, network management station Euro software which runs on the manager. A managed device is a network node that implements an SNMP interface that allows unidirectional or bidirectional access to node-specific information. Managed devices exchange node-specific information with the NMSs. Sometimes called network elements, the managed devices can be any type of device, including, but not limited to, routers, access servers, switches, bridges, hubs, IP telephones, IP video cameras, computer hosts, and printers. An agent is a network management software module that resides on a managed device. An agent has local knowledge of management information and translates that information to or from an SNMP-specific form. A network management station executes applications that monitor and control managed devices. NMSs provide the bulk of the processing and memory resources required for network management. One or more NMSs may exist on any managed network. Management information base. SNMP itself does not define which information a managed system should offer. Rather, SNMP uses an extensible design, where the available information is defined by management information bases. MIBs describe the structure of the management data of a device subsystem. They use a hierarchical namespace containing object identifiers. Each OID identifies a variable that can be read or set via SNMP. MIBs use the notation defined by Structure of Management Information version 2, a subset of ASN1. Protocol details. SNMP operates in the application layer of the Internet Protocol Suite. The SNMP agent receives requests on UDP port 161. The manager may send requests from any available source port to port 161 in the agent. The agent response will be sent back to the source port on the manager. The manager receives notifications on port 162. The agent may generate notifications from any available port. When used with transport layer security or datagram transport layer security, requests are received on port 10161 and traps are sent to port 10162. SNMP v1 specifies 5 core protocol data units. 2 other PDUs, get bulk request and inform request, were added in SNMP v2 and carried over to SNMP v3. All SNMP PDUs are constructed as follows. The 7 SNMP protocol data units are as follows: GET request, a manager to agent request to retrieve the value of a variable or list of variables. Desired variables are specified in variable bindings. Retrieval of the specified variable values is to be done as an atomic operation by the agent. A response with current values is returned. Set request, a manager-to-agent request to change the value of a variable or list of variables. Variable bindings are specified in the body of the request. Changes to all specified variables are to be made as an atomic operation by the agent. A response with new values for the variables is returned. GetNext request, a manager-to-agent request to discover available variables and their values. Returns a response with variable binding for the lexicographically next variable in the MIB. The entire MIB of an agent can be walked by iterative application of GetNext request starting at OID 0. Rows of a table can be read by specifying column OIDs in the variable bindings of the request. GetBulk request, optimized version of GetNext request. A manager-to-agent request for multiple iterations of GetNext request. Returns a response with multiple variable bindings walked from the variable binding or bindings in the request. PDU-specific non-repeaters and max repetitions fields are used to control response behavior. GetBulk request was introduced in Snmp v2. Response returns variable bindings and acknowledgement from agent to manager for GetRequest, SetRequest, GetNext request, GetBulk request and inform request. Error reporting is provided by error status and error index fields. Although it was used as a response to both gets and sets, this PDU was called GetResponse in Snmp v1. Trap, asynchronous notification from agent to manager. Snmp traps enable an agent to notify the management station of significant events by way of an unsolicited Snmp message. Includes current sys uptime value, an OID identifying the type of trap and optional variable bindings. Destination addressing for traps is determined in an application-specific manner, typically through trap configuration variables in the MIB. The format of the trap message was changed in Snmp v2 and the PDU was renamed Snmp v2 trap. While in classic communication the client always actively requests information from the server, Snmp allows the additional use of so-called traps. These are data packages that are sent from the Snmp client to the server without being explicitly requested. Inform request, acknowledge asynchronous notification. This PDU was introduced in Snmp v2 and was originally defined as manager-to-manager communication. Later implementations have loosened the original definition to allow agent-to-manager communications. Manager-to-manager notifications were already possible in Snmp v1, but as Snmp commonly runs over UDP where delivery is not assured and dropped packets are not reported, delivery of a trap was not guaranteed. Inform request fixes this by sending back an acknowledgement on receipt. Development and usage, version 1, Snmp version 1 is the initial implementation of the Snmp protocol. Snmp v1 operates over protocols such as User Datagram Protocol, Internet Protocol, OSI Connectionless Network Service, Apple Talk Datagram Delivery Protocol, and Novell Internet Packet Exchange. Snmp v1 is widely used and is the de facto network management protocol in the Internet community. The first RFCs for Snmp, now known as Snmp v1, appeared in 1988, RFC 1065AA Euro Structure and Identification of Management Information for TCP/IP-based Internets, RFC 1066AA Euro Management Information Base for Network Management of TCP/IP-based Internets, RFC 1067AA Euro A Simple Network Management Protocol. These protocols were obsoleted by RFC 1155AA Euro Structure and Identification of Management Information for TCP/IP-based Internets, RFC 1156AA Euro Management Information Base for Network Management of TCP/IP-based Internets, RFC 1157AA Euro A Simple Network Management Protocol. After a short time, RFC 1156 was replaced by the more often used, RFC 1213AA Euro version 2 of Management Information Base for Network Management of TCP/IP-based Internets. Version 1 has been criticized for its poor security. Authentication of clients is performed only by a community string, in effect a type of password, which is transmitted in clear text. The 80s design of Snmp v1 was done by a group of collaborators who viewed the officially sponsored OSINTF effort as both unimplementable in the computing platforms of the time as well as potentially unworkable. Snmp was approved based on a belief that it was an interim protocol needed for taking steps towards large-scale deployment of the Internet and its commercialization. In that time period, Internet standard authentication security was both a dream and discouraged by focused protocol design groups. Version 2c, Snmp v2, revises version 1 and includes improvements in the areas of performance, security, confidentiality, and manager-to-manager communications. It introduced Get Bulk Request, an alternative to iterative GetNext requests for retrieving large amounts of management data in a single request. However, the new party-based security system in Snmp v2, viewed by many as overly complex, was not widely accepted. This version of Snmp reached the proposed standard level of maturity, but was deemed obsoleted by later versions. Community-based Simple Network Management Protocol version 2, or Snmp v2c, is defined in RFC 1901 or FC 1908. Snmp v2c comprises Snmp v2 without the controversial new Snmp v2 security model, using instead the simple community-based security scheme of Snmp v1. This version is one of relatively few standards to meet the IETF's draft standard maturity level, and was widely considered the de facto Snmp v2 standard. It too was later obsoleted, by Snmp v3. User-based Simple Network Management Protocol version 2, or Snmp v2u, is defined in RFC 1909 or FC 1910. This is a compromise that attempts to offer greater security than Snmp v1, but without incurring the high complexity of Snmp v2. A variant of this was commercialized as Snmp v2, and the mechanism was eventually adopted as one of two security frameworks in Snmp v3. Snmp v1 and Snmp v2c interoperability, as presently specified, Snmp v2c is incompatible with Snmp v1 in two key areas, message formats and protocol operations. Snmp v2c messages use different header and protocol data unit formats from Snmp v1 messages. Snmp v2c also uses two protocol operations that are not specified in Snmp v1. Furthermore, RFC 2576 defines two possible Snmp v1/v2c coexistence strategies, proxy agents and bilingual network management systems. Proxy agents: an Snmp v2 agent can act as a proxy agent on behalf of Snmp v1 managed devices, as follows. An Snmp v2 NMS issues a command intended for an Snmp v1 agent. The NMS sends the Snmp message to the Snmp v2 proxy agent. The proxy agent forwards GetNext, and set messages to the Snmp v1 agent unchanged. Get bulk messages are converted by the proxy agent to GetNext messages and then are forwarded to the Snmp v1 agent. The proxy agent maps Snmp v1 trap messages to Snmp v2 trap messages and then forwards them to the NMS. Bilingual Network Management System. Bilingual Snmp v2 network management systems support both Snmp v1 and Snmp v2. To support this dual management environment, a management application in the bilingual NMS must contact an agent. The NMS then examines information stored in a local database to determine whether the agent supports Snmp v1 or Snmp v2. Based on the information in the database, the NMS communicates with the agent using the appropriate version of Snmp. Version 3. Although Snmp v3 makes no changes to the protocol aside from the addition of cryptographic security, it looks much different due to new textual conventions, concepts, and terminology. Snmp v3 primarily added security and remote configuration enhancements to Snmp. Due to lack of security with the use of Snmp, Network administrators were using other means, such as Telnet for configuration, accounting, and fault management. Snmp v3 addresses issues related to the large-scale deployment of Snmp, accounting, and fault management. Currently, Snmp is predominantly used for monitoring and performance management. Snmp v3 defines a secure version of Snmp and also facilitates remote configuration of the Snmp entities. Snmp v3 provides a secure environment for the management of systems covering the following: identification of Snmp entities to facilitate communication only between known Snmp entities. Each Snmp entity has an identifier called the Snmp, and Snmp communication is possible only if an Snmp entity knows the identity of its peer. Traps and notifications are exceptions to this rule. Support for security models. A security model may define the security policy within an administrative domain or an intranet. Snmp v3 contains the specifications for USM. Definition of security goals, where the goals of message authentication service include protection against the following: modification of information, protection against some unauthorized Snmp entity altering in-transit messages generated by unauthorized principal. Masquerade, protection against attempting management operations not authorized for some principal by assuming the identity of another principal that has the appropriate authorizations. Message stream modification, protection against messages getting maliciously reordered, delayed, or replayed to affect unauthorized management operations. Disclosure, protection against eavesdropping on the exchanges between Snmp engines. Specification for USM. USM consists of the general definition of the following communication mechanisms available: communication without authentication and privacy, communication with authentication and without privacy, communication with authentication and privacy. Definition of different authentication and privacy protocols. Currently, the MD5 and SHA authentication protocols and the CBCDES and CFBAS 128 privacy protocols are supported in the USM. Definition of a discovery procedure, to find the Snmp of an Snmp entity for a given transport address and transport endpoint address. Definition of the time synchronization procedure, to facilitate authenticated communication between the Snmp entities. Definition of the Snmp framework MIB, to facilitate remote configuration and administration of the Snmp entity. Definition of the USM MIBs, to facilitate remote configuration and administration of the security module. Definition of the VACM MIBs, to facilitate remote configuration and administration of the access control module. The Snmp v3 focuses on two main aspects, namely security and administration. The security aspect is addressed by offering both strong authentication and data encryption for privacy. The administration aspect is focused on two parts, namely notification originators and proxy forwarders. Snmp v3 defines a number of security-related capabilities. The initial specifications defined the USM and VACM, which were later followed by a transport security model that provided support for Snmp v3 over SSH and Snmp v3 over TLS and DTLS. USM provides authentication and privacy functions and operates at the message level. VACM determines whether a given principal is allowed access to a particular MIB object to perform specific functions and operates at the PDU level. TSM provides a method for authenticating and encrypting messages over external security channels. Two transports, SSH and TLS-DTLS, have been defined that make use of the TSM specification. Security has been the biggest weakness of Snmp since the beginning. Authentication in Snmp versions 1 and 2 amounts to nothing more than a password sent in clear text between a manager and agent. Each Snmp v3 message contains security parameters which are encoded as an octet string. The meaning of these security parameters depends on the security model being used. Snmp v3 provides important security features, confidentiality, encryption of packets to prevent snooping by an unauthorized source, integrity, Message integrity to ensure that a packet has not been tampered while in transit, including an optional packet replay protection mechanism. Authentication, to verify that the message is from a valid source. As of 2004, the IETF recognizes Simple Network Management Protocol version 3 as defined by RFC 3411 or FC 3418 as the current standard version of Snmp. The IETF has designated Snmp v3 a full Internet standard, the highest maturity level for an RFC. It considers earlier versions to be obsolete. In practice, Snmp implementations often support multiple versions, typically Snmp v1, Snmp v2c, and Snmp v3. Implementation issues: Snmp implementations vary across platform vendors. In some cases, Snmp is an added feature, and is not taken seriously enough to be an element of the core design. Some major equipment vendors tend to overextend their proprietary command line interface-centric configuration and control systems. Snmp's seemingly simple tree structure and linear indexing may not always be understood well enough within the internal data structures that are elements of a platform's basic design. Consequently, processing Snmp queries on certain datasets may result in higher CPU utilization than necessary. One example of this would be large routing tables, such as BGP or IGP. Some Snmp values require specific knowledge of table indexing schemes, and these index values are not necessarily consistent across platforms. This can cause correlation issues when fetching information from multiple devices that may not employ the same table indexing scheme. Resource indexing: modular devices may dynamically increase or decrease their Snmp indices whenever slotted hardware is added or removed. Although this is most common with hardware, virtual interfaces have the same effect. Index values are typically assigned at boot time and remain fixed until the next reboot. Hardware virtual entities added while the devices live may have their indices assigned at the end of the existing range and possibly reassigned at the next reboot. Network inventory and monitoring tools need to have the device update capability by properly reacting to the cold start trap from the device reboot in order to avoid corruption and mismatch of polled data. Index assignments for an Snmp device instance may change from poll to poll mostly as a result of changes initiated by the system administrator. If information is needed for a particular interface, it is imperative to determine the Snmp index before retrieving the data needed. Generally, a description table like if DESCR will map a user-friendly name like serial 0/1 to an Snmp index. However, this is not necessarily the case for a specific Snmp value, and can be arbitrary for an Snmp implementation. Security implications: Snmp versions 1 and 2c are subject to packet sniffing of the clear text community string from the network traffic, because they do not implement encryption. All versions of Snmp are subject to brute force and dictionary attacks for guessing the community strings, authentication strings, authentication keys, encryption strings, or encryption keys, because they do not implement a challenge-response handshake. Although Snmp works over TCP and other protocols, it is most commonly used over UDP that is connectionless and vulnerable to IP spoofing attacks. Thus, all versions are subject to bypassing device access lists that might have been implemented to restrict Snmp access, though Snmp v3's other security mechanisms should prevent a successful attack. Snmp's powerful configuration capabilities are not being fully utilized by many vendors, partly because of a lack of security in Snmp versions before Snmp v3 and partly because many devices simply are not capable of being configured via individual MIB object changes. Snmp tops the list of the SANS Institute's common default configuration issues with the issue of default Snmp community strings set to a Euro-public, a Euro-unregistered trademark and a Euro-private, a Euro-unregistered trademark, and was number 10 on the SANS Top 10 Most Critical Internet Security Threats for the year 2000. Auto-discovery. Snmp by itself is simply a protocol for collecting and organizing information. Most toolsets implementing Snmp offer some form of discovery mechanism, a standardized collection of data common to most platforms and devices, to get a new user or implementer started. One of these features is often a form of automatic discovery, where new devices discovered in the network are polled automatically. For Snmp v1 and Snmp v2c, this presents a security risk, in that your Snmp read communities will be broadcasting clear text to the target device. While security requirements and risk profiles vary from organization to organization, care should be taken when using a feature like this, with special regard to common environments such as mixed-tenant data centers, server hosting and co-location facilities, and similar environments. RFC references. RFC 1155AA Euro Structure and Identification of Management Information for the TCP/IP-based Internets, RFC 1156AA Euro Management Information Base for Network Management of TCP/IP-based Internets, RFC 1157AA Euro A Simple Network Management Protocol, RFC 1213AA Euro Management Information Base for Network Management of TCP/IP-based Internets, MIBE, RFC 1452AA Euro Coexistence between version 1 and version 2 of the Internet Standard Network Management Framework, RFC 1901AA Euro Introduction to Community-based Snmp v2, RFC 1902AA Euro Structure of Management Information for Snmp v2, RFC 1908AA Euro Coexistence between version 1 and version 2 of the Internet Standard Network Management Framework, RFC 2570AA Euro Introduction to version 3 of the Internet Standard Network Management Framework, RFC 2578AA Euro Structure of Management Information version 2, RFC 3410AA Euro Introduction and Applicability Statements for Internet Standard Management Framework, 62 Sautom and Principe Dobras, RFC 3411AA. Euro an Architecture for Describing Simple Network Management Protocol Management Frameworks, RFC 3412AA Euro Message Processing and Dispatching for the Simple Network Management Protocol, RFC 3413AA Euro Simple Network Management Protocol Applications, RFC 3414AA Euro User-Based Security Model for version 3 of the Simple Network Management Protocol, RFC 3415AA Euro View-Based Access Control Model for the Simple Network Management Protocol, RFC 3416AA Euro version 2 of the Protocol Operations for the Simple Network Management Protocol, RFC 3417AA Euro Transport Mappings for the Simple Network Management Protocol, RFC 3418AA Euro Management Information Base for the Simple Network Management Protocol, RFC 3430AA Euro Simple Network Management Protocol over Transmission Control Protocol Transport Mapping, RFC 3584AA Euro Coexistence between version 1, version 2, and version 3 of the Internet Standard Network Management Framework, RFC 3826AA Euro the Advanced Encryption Standard Cipher Algorithm in the Snmp User-Based Security Model, RFC 5343AA Euro Simple Network Management Protocol Context Engineered Discovery, RFC 5590AA Euro Transport Subsystem for the Simple Network Management Protocol, RFC 5591AA Euro Transport Security Model for the Simple Network Management Protocol, RFC 5592AA Euro Secure Shell Transport Model for the Simple Network Management Protocol, RFC 5608AA Euro Remote Authentication Dial and User Service Usage for Simple Network Management Protocol Transport Models, RFC 6353AA Euro Transport Layer Security Transport Model for the Simple Network Management Protocol. Further reading, Douglas Morrow, Kevin Schmidt. Essential SNMP, 2nd edition O'Reilly Media. PA 462. ISBN A0596008406. See also, Agent X, a sub-agent protocol for SNMP, CMIP over TCP/IP, Common Management Information Protocol, a management protocol by ISO-OSI used by telecommunications devices, Common Management Information Service, IEC 62379, Management Information Base, Net SNMP, an open-source reference implementation of SNMP, netconf, a protocol which is an XML-based configuration protocol for network equipment, network monitoring comparison, object identifier, remote monitoring, simple gateway monitoring protocol, an obsolete protocol replaced by SNMP, SNMP simulator, references. External links, Simple Network Management Protocol at DMOZ.